So, welcome back everybody to this brand new, fresh, and interesting episode. And today we'll be learning about the most awaited topic of the atomic model that has been recently developed. And the first comes the Schrodinger's wave-front equations, and from that everything has been so much rapidly developing. And at the second number comes Niels Bohr's atomic model, and that is a very beautiful model that even a 11th grade student can understand. So yes, let us start now. And first of all, Neil Bohr actually gave some postulates, that is some assumptions, and there are no actual answers to these postulates. So we'll make it to go. So let us first discuss the drawbacks of Rutherford's model so as to understand. So the Rutherford's model said that the electron is in the orbit, and now if it is revolving in a circular orbit, then according to Maxwell's equations, it should emit a particular type of light while it is revolving in a particular circular orbit. We will discuss the Maxwell's equations and any further parts and episodes on it. But right now, you just have to know that the Maxwell's equations define that if a particular object is moving in a circular orbit, then it must emit a type of color or a wavelength, which, according to the Rutherford's model, if it should, then it should lose its energy and then it should go and meet inside, which they assume. But we have never seen such kind of thing happening. So that is where the Rutherford's model failed to explain. And then came Neil Bohr's model. There were other types of drawbacks that it had, like you can say, but the Neil Bohr model covered all of its drawbacks. Now let us know what. So first of all, Bohr's atomic model said that electron revolved in circular orbit. The second one, when it jumps from lower to higher energy state I'm writing as, and these circular orbits are called as stationary orbits. ONARY orbits, which is what he called it. And these are allowed orbits. There are only a selected orbits which the electron can revolve, which wasn't a kind of thing that was restricted. Like, this is a kind of thing that restricted the revolving of electron in any type of orbit, but this was the thing that wasn't considered in the Rutherford's atomic model. When it goes from lower energy state to high energy states, it accepts energy, and when it goes from higher to lower, it radiated energy that was in the form of photons. And we have discussed about the discovery of photons and its mechanism and what wavelength of photon can be and all the properties and characteristics of photon in the first and the second episode. So do watch that if you don't know. So let's go to the next. The total energy in a particular orbit is constant. The photon is that when an electron is in a particular stationary orbit, does not jump, then it does not radiate any energy. I'll write it. And now, for the convenience, let us discuss the fifth and the most important, that is the Bohr's quantization law, that is mvr equals to integral multiple of h upon 2 pi. This is the most important thing. Even if you die, you should be able to answer this question. That hard important this thing is. So, what is this MVR? It is angular momentum in an orbit. I'll call stationary orbit as an orbit. And this is h, is Planck's constant, that is 6.6 into 10 to the power minus 34. And this is our pi, that is 22 by 7, as everybody knows. So now let us understand the Bohr's model. Note, only applicable, this model is only applicable for hydrogen like species, that is one proton and one electron, as we'll see why in the further upcoming content. Now, so now let us draw a diagram that would be very useful. Now this is our hydrogen atom nucleus, and this is our electron stationary orbit. This is a stationary orbit, and here is our electron. This is our proton. And now on this electron, the attractive force is working, that is the gravitation, the Coulomb's attractive force, which can be written as K Q1 Q2 by R with a minus sign, showing that it is inwards. But as it is a centripetal force, we will not write the minus sign and equate it with the centripetal force mv square by R. Here comes our R square. And now let us substitute ahead that for generalizing the case, we are writing K Q1, that is the charge of a proton, that is E. Then the second is the charge of an electron, that is ZE upon R square. Then cutting this R square and R, we only remain with an R over here, and this is equals to m into velocity of the electron, the square. I'll write it like this. And now, okay, so now the mass of the electron, that is, we write the centripetal force for the revolving and rotating object. And now the radius can be found out by R equals to kze square by mave square. But now we know that mvr equals to nh upon 2 pi, that is meve, that meve we are writing. And now R equals to nh upon 2 pi meve. Now equating 1 with 2, we get nh upon 2 pi meve equals to kze square upon meve square. Now meve cuts, So only one VE remains. So VE equals to KZ E square into 2 pi upon NH. This is a 3. First of all, we have derived the velocity, and now let us now substitute this velocity into equation 2. Yes, no, we'll substitute in equation 1 as there is no square over here, we see. So R equals to NH upon 2 pi into V KZ E square 2 pi upon NH. Therefore R is equals to N square H square upon 2 pi K Z E square and okay 4 pi square as 2 pi K Z square E square mass of electron, which after putting the values is equals to 0.529 N square by Z in angstrom. This is what we need to remember once again. And the velocity, it is equals to C upon 137 times Z by N meters per second. Yes, and we got this velocity over here in this equation, which you must remember right over here. Yes, this equation we found the velocity. And now let us understand a bit more about the atomic model. Let us find out the time period of electron in an orbit. So we know the radius, we know the velocity. So we know V equals to velocity is equals to distance covered per unit time. Over here velocity is 2 pi r by t. We know the velocity, we know 2 pi r. The value of r also is known and v is also known. So we can get t equals to 2 pi r by v. Upon substituting the values, we get 2 pi into 0.53 n square by z upon cz. Oh, here we have derived cz by n, c upon 137 z by n. So it becomes, we just want to know the proportionality, it becomes n cube upon z square. No need for the actual values at all. Now let us derive proportionality between Z, N and total energy. So number 1 is kinetic energy. It is equals to half mv square, that is equals to half into mass of electron into v, that is c upon 137, in and z by n the whole square, that is half me. This is also constant, z square by n square. So kinetic energy is equal to z square, not equal to, sorry, directly proportional to z square by n square. And now the potential energy, just a minute, the potential energy is equals to k e z e upon r. This is the potential energy. So U equals to kz e square upon 0.529 n square by z. Therefore U is directly proportional to z square by n square. Yes. And now if we see, total energy will also be directly proportional to z square by n square, and the ratio between total energy, potential energy and kinetic energy is that kinetic energy is 1 minus 1 and 2. This is the ratio. Yes. And the formula for total energy is minus 13.2 z square by n square. This is in EV. Now let us understand some of the final content of the chapter, the Bohr's atomic model, and that is the emission of radiation. So there are two types of spectrums. I'll draw them now. Yes, so I'll write this one as continuous and this one as characteristic. What is a continuous spectrum? It is like here it is dark, then here it becomes faint, and the gradient is constant. Over here it is like, over here we see a line, then over here we see some part of line, over here, then over here. It is not constant. This is emission. And for the shocking fact, the emission spectrum and the absorption spectrum were studied before the Bohr's atomic model was put forth. And so, a Bohr's atomic model was, after experimenting with Bohr's atomic model, putting down the values, it satisfied the conditions for the emission spectrum and absorption spectrum, and the values were quite closer to each other, and we can say nearly about accurate, and thus we can conclude that this model was applicable for hydrogen like species without any flaw. So what did Bohr's model say? The change in energy level is equal to energy of photon, as we saw over here in the first postulate. In this postulate, As we have seen over here, if we jump from higher to lower, it radiates energy in the form of photons. So how would have I remembered this? So let us see our atomic model for it. So it's like there is another virtual orbit present over here, which is accessible only if you have a certain amount of money. So for example, let us assume you have an X amount of money over here and this needs a Y amount of money. Now you have gained some K amount of money, so that to equate it with equal to Y, and so you jump over here. But now that you do not actually belong in this orbit, you are thrown out of this orbit once again, and you lose the K amount of energy, and you have again the X amount of energy X with you. So this is what our model said, and which on experimentation made result into the energy spectrum and the seeing of photon. So E2 minus E1, E2 minus E1 equals to hc by lam. So we can better write it in the type form of frequency h nu. E2 minus E1 upon h equals to nu. Now that we have known, let us put the value of E2 1 upon h. Yes, so now let us put in the values. 1 by h, E2, that is minus 13.6 z square upon n2 square, minus E1, that is minus 13.6 z square upon n1 square, is equal to nu. So 1 by h into will take minus 13.6 z square as common, and then we get minus 1 upon n2 square plus 1 upon n1 square is equals to nu. And now nu can be written as minus 13.6 z square by h 1 upon n1 square minus 1 upon n2 square. Yes. And for this shocking fact, what the scientists earlier had found out, they were using this particular formula for the frequency, and that was Rydberg's constant z square 1 upon n1 square minus 1 upon n2 square. So now what they meant to say was minus 13.6 upon h was equals to Rydberg's constant, which was equal to 1.097 into 10 to the power minus 7 meter inverse. And if we calculate the values, this is exactly what we get. So it gave a firm belief that yes, all the things that we have been working on are correct. And now let us see the graph. So if we put in the values and start drawing a energy level diagram, then it goes something like this. Yes, this is our ground state. This is our first excited state. This is our second excited state. This is our third. This is our fourth, and above going on till infinity. Now the value is minus 13.6, then minus 3.4, then minus 1.5, and at infinity we have assumed that it is 0 eV. and accordingly we have set. And over here in this state n is equals to 1, n is equals to 2, n is equals to 3, n is equals to 4, and so on till a infinity. And now this line rays I'll draw from infinity. If we bring an electron to ground state, the ground state, let us use another color for this. Yes. Over here 2, 3, 4, then each and every type of photon would emit a different color light, and this was discovered before the Bohr's atomic model, but now that we are studying it after the Bohr's atomic model, we are getting a clear and concise understanding of it. And another thing to note is 1 upon Rydberg's constant is 911 angstrom. Yes, this is also important. Now let us continue over here. The Lyman series is where n1 is equals to 1 and n2 is greater than 1. Then comes Balmer series where n1 is 2. Then the Paschen series where n1 is 3. Then the bracket series where n1 is 4. Then the P fund series where n1 is 5, and simultaneously n2 is greater than 2, 4 is greater than 4, and 5 is greater. So what this meant was that we can bring an electron from any, for example, if we take the Lyman series, we can take an electron from the second excited state to the first excited state. Let us draw it in another color. Second excited state to the first excited state, or the third excited state to the first excited state, or the infinite excited state to the first excited state. That is what it meant. And each and every type of photon meant a different color, and hence this different type of series was found over there. And that is it. We are at the end of Bohr's atomic model. Meet you in the next episode. Yes, till then, thank you and bye bye.